Good morning. I'd like to start talking about the concept of work as it's defined in physics. I'm going to make two of these videos, one of them introducing the idea and then applying it to springs, Hooke's law. The other will be Newton's universal law of gravitation and the work done by an expanding gas. The simplest of all possible situations is when you have an object being moved along a straight line by a force that points in that direction. In this simple case, for instance, there might be a force of 30 pounds acting off to the right, and using this corner as my reference point, the object might be moved 10 feet. The amount of work done is force times distance, 30 times 10, 300 foot-pounds. And what we're going to be doing, things are a little bit more complicated than that. We are going to have some variable x that represents position, where something is located at. Changes in x will represent how far the object is moving. Also, we'll have a force. The force will still be acting along the direction that the object moves, but the magnitude of the force may vary. It may change from location to location. Because of that, just saying force times distance is not going to give us an answer. Not a right answer, anyway. I want to imagine starting at location specified by x equal a and ending at x equal b. Since the force can vary from point to point, I need to do some sort of calculation, some sort of situation in which I can regard the force as very nearly being constant. We'll follow the same strategy that we've been following. I'll divide the range of x values from a to b up into a large number of much smaller ones. I'll call the width of one of these delta x with an index showing which chunk I'm talking about. Within each of these smaller pieces, I'm going to select an x number, c number I. I'm going to make these subdivisions so small that the force doesn't have much opportunity to change its value from what it is to ci to some other value. So within this chunk, I'm going to approximately say the force is always equal to F evaluated at ci. The work done on this one individual piece is approximately F at ci times delta xi. As surely comes to no surprise to anyone by this stage of the game, we add up all of these pieces, then take the limit as all of the delta x's go to 0 to make our estimates perfect. This is the amount of work done traveling from x equal a to x equal b. Of course, that's the definition of an integral. If I have a force that depends on some position variable, x, and I start at x equal a, end at x equal b, then the amount of work done is the integral of the force with respect to position, starting at the initial value of position, ending at the end value. Previously, when we write an integral like that, it might represent an area or a volume or an arc length. Now, this doesn't mean any of those things. This is an amount of work. It's amount of energy. The first of these examples I want to look at involves springs. There's a thing called Hooke's Law, named after Robert Hooke, that says if you have a spring, then depending on the spring, there is a constant, K, so that the force needed to stretch the spring a certain length from its natural or equilibrium length is constant times how much you stretched it. So if I stretched the spring 3 feet from its equilibrium length, the force needed would be this constant multiplied by 3. Obviously, as x gets bigger, the force gets bigger as well. I want to work through an example that illustrates why you can't do something, and then we'll see what you actually do. I want to imagine taking a spring whose force equation is force equals 6x, so that the k is equal to 6. I'm going to start at its equilibrium length, and I'm going to stretch it 4 feet. For this problem, we'll take the force to be in pounds, and the distances to be in feet. At the end of this situation, the force that needs to be exerted on the spring to hold it here is 6 times the displacement from equilibrium, 6 times 4, which is 24 pounds of force. You stretched it 4 feet. It's tempting to say that the work must be just force times distance, 24 times 4, which is 96 foot-pounds. But that's not right, as I want to illustrate here. I can imagine doing this stretching as a sequence of things. First, we stretch 1 unit, then we stretch another unit to reach x equals 2, then another to get to x equal 3, and then another to get to x equal 4. Each one of these little chunks corresponds to changing the x value involved by 1 unit. Now, within each one of these chunks, though, I'm going to pick a representative c number so that I can estimate the force over the entire bit. I'm going to take the biggest x number within each chunk. The force needed to stretch the spring to a given position is 6 times the position number. So here I'm going to have 6 times 1, 6 times 2, 6 times 3, and 6 times 4. So early on, only 6 pounds of force were needed to change the position by 1 unit, but then 12 were needed, and 18, and only at the very end was 24 needed. I need to multiply each of these force values by the corresponding delta x, all of which are 1 in this case, which will make life easy. My rough estimate for the amount of work needed to go from equilibrium to x equal 4 is 60 foot-pounds. This is only a rough approximation, of course, since I'm using pretty good-sized pieces, but even so, 60 is considerably different from 96. On the next page, we'll see the exact amount of work. So we have the same situation. The force is 6 times x, where x is the displacement of the spring from equilibrium position. X is going to vary between 0 and 4, so the force will vary also. What we have figured out in the first part of this video is to get the amount of work, what I need to do is I need to integrate the force with respect to the variable that tells me my location. The force is 6x. The relevant x's range from 0 to 4, and the integral is straightforward to do now. The result is the amount of work needed was 48 foot-pounds. This kind of problem, it takes a force of 20 pounds to stretch a spring 3 feet from its natural length, from its equilibrium length. How much work was done? This kind of question seems almost mean-spirited. Whoever cooked this kind of question up is hoping that you will knee-jerk. You'll see that you've got a force of 20 pounds and a displacement of 3 feet. 20 times 3 is 60 foot-pounds. That's completely wrong because the force isn't constant. On the one hand, the amount of work that's going to be needed is an integral. We just figured that out. I put my initial x value in, my ending x value. I'm integrating with respect to x, which is a variable that represents how much the spring has been stretched. It tells me a location. And the thing that I have to integrate is k times x. If we knew what the k was, this would be a really easy problem, but we don't. The meaning of that sentence at the beginning, it takes a force of 20 pounds to stretch a spring 3 feet, does not tell you the amount of work done directly. You can't do force times distance. What it does tell you is this: if you know Hooke's law, it'll let you figure out what the k is. Hooke's law says the relationship between the force needed and the amount that you're stretching the spring from its natural length is force is constant times x. When F, the force, is 20 pounds, that corresponds to the x being 3. That tells you that 20 is k times 3, which immediately tells you that the k is 20/3. So the integral that you need to do in order to calculate the amount of work is the integral from 0 to 3 of 20/3 times x dx. Doing this integral is straightforward. An antiderivative is 20/3 times 1/2 x squared. I'll combine the fractions into 10/3 times x squared. Putting the limits of integration in, we found out that the amount of work needed is actually 30 foot-pounds. You can make many variations on a theme of this kind of question. Here's one. 500 foot-pounds of work is needed to stretch a spring from x equals 4 to x equals 6. How much work is done stretching the spring from x equals 0 to x equals 4? There's a sentence, and then there's a question. I'm going to think about the question first. I've got this spring. It obeys Hooke's law. I'm going to start at x equals 0, end at x equals 4, integrating the force, and the result will be the amount of work that I'm interested in. Based on what we said previously, the work is just going to be the integral from 0 to 4 of the spring force, k times x, with respect to x. If I literally knew the value of k, we would be in business. The only additional piece of information that I have is this sentence up at the front, where it says 500 foot-pounds of work is needed to stretch a spring from x equals 4 to x equals 6. What hopefully will happen is That will give me enough information to figure out what the K is, and then life will be easy. The amount of work needed to stretch the spring from x equals 4 to x equals 6 is this integral. But the first bit, this sentence, says that if I were able to calculate this integral, the answer must come up to be 500. This is going to end up telling me something. If I evaluate the integral, the meaning of that first sentence, when all the dust finally settles, is the K must be 50. Having figured out that K is 50, the amount of work needed to stretch from x equals 0 to x equals 4 is the integral from 0 to 4, K times x, 50 times x, with respect to x. And after evaluating the integral, we found out that the amount of work needed is 400 foot-pounds. As I said, we're going to look at 3 different types of work problems. Hooke's law and springs is the first type. The other 2 types involve gravitation and the work done by an expanding gas. This will be coming up in the next video. In the meantime, I hope that everybody has a good day, and I'll talk to you again soon.